Alright, hello class. In this video we're going to be talking about graphing functions using calculus. So this basically just rounds out everything we've done so far from critical points on up to concavity, puts it all together and lets us practice it all by graphing functions from the ground up. That's essentially what we'll be doing. Okay, and I think I get pushback on this sometimes because with the advent of graphing calculators, there are a lot of people who think, or even graphing software, there are a lot of people who kind of think that this is sort of an archaic subject, graphing things by hand, sketching graphs by hand. However, there's an argument to make that while that may be true, this is also good practice in an environment where you're finding critical points, you're finding inflection points, you're finding intervals of increase and decrease, and then you're doing something with it all in sort of an environment that is kind of nebulous before we start actually jumping into application problems. So that's the next step, is more like word problems. So this gives you practice doing all this stuff sort of again before we start really focusing on those application problems. Now, there's also another reason we might want to do this, and we'll get to that in the first example we look at. And I'm just going to jump to examples because we've actually done all the heavy lifting here. We have done everything we need to actually do what we need to do in this particular lesson. It's more a matter of like what the process is. So through the examples I will describe the process. Okay, and in this first example will give us one of the other reasons why we might need to know this sort of methodology. Alright, so to start with, let's use calculus to sketch a complete graph of f of x equals x cubed over 3 minus 400x. Alright, so if we were to jump straight to software, so if you were to just plug this into your graphing calculator under the standard window, or go to some graphing software like I have here, and we just graph this function, all we see is this line here, and it's kind of difficult to see what's going on. In fact, if we start zooming this out, okay, we see what looks like just vertical lines, right? So instead of just futzing around with this window, okay, again, I've zoomed out pretty far and this still looks like just vertical lines, right? Now it shouldn't be because this is a nice polynomial, should be continuous and smooth everywhere. So that's not the case. So what we're going to do is just use calculus to find all of the important information. Okay, so what we want to find is we want to find x and y intercepts, right? We want to find critical points and intervals of increase and decrease, right? And this should also lead us to the extrema. So this is maxes and mins as well. Okay. We want to find inflection points, or we want to find intervals of concavity, right, and inflection points. And one thing we haven't really spent a lot of time doing here is find all the y values of these things. And then we'll use all this information to graph. Okay? Now, notice here I'm saying to sketch a graph. So when we're sketching this by hand, no one's looking for perfection, okay? We're mainly looking for just all the main pieces to be in the right spot. Okay, so let's approach this now. Alright, so before I start finding intercepts, I actually start with critical points and the first and second derivative. Okay, so that's always my step one, is I'm going to find f prime and f double prime. Okay, So f prime of x is going to be x squared minus 400. Okay, and then f double prime of x is just going to be 2x. All right, so now that I've found f prime and f double prime, now I'm going to find the critical points. And since we started with a polynomial, our derivative is a polynomial, so we don't have any undefined critical points. So we really just need to set x squared minus 400 equal to 0. So really this is x squared is equal to 400. So x is equal to plus or minus 20. All right. Now, here's where I was talking about in the last lesson where now that we already have to find the second derivative anyway, we might as well use the second derivative test. So we found the critical points. Now I'm going to use the second derivative test to analyze these. Okay, and that's just because we already have the second derivative, and it will be quite easy to plug these into f double prime, right? So f double prime of negative 20 will be negative 40. That's negative. So second derivative negative, that means concave down, which is a frown. So that means that this negative 20 corresponds with a maximum. Okay, while when we plug in the positive 20, we'll get the exact opposite happening because this is just 2x. So we will get positive 40. That's concave up. That means we have a u. That means x equals 20 is a minimum. All right, so we found the x values. I'm going to basically leave it there for the time being. Okay, I'm going to come back later and find the y values. There's no real hurry here. All right, so now we're going to try and find the concavity. We're going to try to find the inflection points and analyze the concavity. Okay, so what we're going to do is set f double prime equal to 0. So f double prime is 2x, so we'll just set that equal to 0 and solve. So x is equal to 0. Now to analyze concavity, we're going to put our 0, and we're going to look at f double prime and tell us about f. Okay, so I'm going to pick, say, negative 1 here for my test value. So f double prime of negative 1 is negative 2. So specifically we're negative. So f is concave down here. Notice we've actually already checked this with, say, negative 20, right? So I could actually say positive 20 here, right? And that's 40. So this is concave up. So actually the nice thing about the second derivative test, it has actually given us our intervals of concavity. So that's one really nice thing about it. Another nice thing about it is it also gives us our intervals of increase and decrease, because if I make another number line and I put negative 20 here and put positive 20 here, so we established that negative 20 is a max and 20 is a min. So we've established that this is a max, this is a min. That means that f, right, goes from, for a max, increasing to decreasing, and for the min goes from decreasing to increasing. So this actually gives us our intervals of increase and decrease for f. Okay? So it turns out that the second derivative test, if we can apply it, gives us a lot of information just right off the bat. Okay? So let's collect a lot of this information here, and then we'll go a little further. All right, so here's some of the information we found already. our max is at x equals negative 20, the min is at x equals, our max is at negative 20, min is at 20, the inflection point is at 0. Okay, so now I want to find the x and y intercepts. So for the y-intercept, that's just a matter of plugging in 0. Right? That's going to be f of 0, which will give us 0. Right? So that's 0, 0 is the y-intercept. To find the x-intercepts, right, that's where you set this equal to 0 and solve. So you actually set the original function equal to 0 to find your x-intercepts. All right, so we can factor out an x here to get, x times x squared over 3 minus 400 equals 0. So x is equal to 0. Well, we should get that because we have a y-intercept that is also 0. Okay, so if a y-intercept is 0, it's also an x-intercept. Okay, and then we will also have x squared over 3 minus 400 is equal to 0. Okay, so x squared is equal to 1200. Right, so x is equal to plus or minus the square root of 1200. Of course, we can actually take the 400 out and get that this is plus or minus 20 times root 3, okay, which is about plus or minus 34.64-ish. Okay, so now that we have all this information, I want to find the y values of everything. Right, so we want to find the y values. So that's really just plugging in every important thing we have into our f and getting the y, right? So it's going to be f of negative 20, f of, well, we already know f is 0, but I'll go ahead and put it, f of 0, f of negative 20, or sorry, positive 20, and we probably need to add, and I say probably, we need to add the negative 34.64 and the positive 34.64 and see what we get. All right, so I'm just going to jump to a calculator to calculate these out. Of course, 0 we've already done, which is 0. And the values here of the x-intercepts, those should be 0 when you plug them in because they're x-intercept. So it should be plus or minus 34.64 comma 0. Okay, so really we're more focused on what's going on with the negative 20 and 20. All right, so plugging in negative 20, we get 5,333.3 repeating. And at 20, we get negative 5,333.3 repeating. This is why we couldn't see this on our software. We would have to zoom out to 5,000 to actually start seeing, before we start seeing some turning points. But even here, it doesn't look like anything's happening. If we now shrink down our x-axis, we can finally start seeing what's happening here. Now, instead, we've done this through analytical means. Okay, now let me show you how we graph this. Say we didn't know what it looked like, and we just wanted to jump, or maybe not jump straight to it, but we want to graph this by hand. Let me show you the method I use. Okay, so here I've collected all of our information, the points and what they are. Right? We have our max, we have our min, we have our inflection point, x-intercept, y-intercept. So notice that 0, 0 is quite a few things. It's an inflection point, x-intercept, and y-intercept, and then this negative 34.64, comma 0, those are our x-intercepts. Okay, so let's make a graph. All right, so here we have a little blank axis I've made. I'm going to mark off some of our important places here. I'm going to say that this is negative 20 and that this is 20. All right, and we have a max here, so I'm just going to say that this is actually the point, right? 5333.3 repeating, and I'm going to match it here for the negative value. Okay, so here is our max. That's the maximum we found. Here's our min. Okay. And then we also found the point 0, 0, which was our inflection point. And then we found some x-intercepts, right? One at negative 34.6 and another one at positive 34.6. Okay, so these are just x-intercepts. All right, so notice here, I've just labeled everything. Now, here's what, or at least here's how I do things, okay? So we need to connect all of these dots, right? So going from left to right, this point needs to go up to this point, then down to this point. Well, notice this is automatically going to make a maximum. In fact, I like to go ahead and fill in an upside down U for a max and a U for a min. Okay, now I might have to adjust the way it looks in a minute. In fact, I need to sort of connect it to this point. Okay, let me do that, and then connect it to this point. Unless I know otherwise, I'm just going to let it continue going down. Then for this U, well, I'm going to connect it smoothly as I can to this inflection point, and then move up here and then let it go without bound this way. Okay, wherever I see a min, I put a U. Wherever I see a max, I put a frown. And then I try my best to connect it all. Now notice, I didn't really worry about concavity because connecting things in this way basically makes this an inflection point. That makes this concave down here and concave up here, which is exactly what we found, right? So as long as you connect those maxes and mins in the most efficient way that you can, it's going to line up, all right? So this is what I mean when I'm asking for a sketch. I'm not asking for anything to be perfect, just to give you the overall idea. And if we compare it to what we have here, that basically lines up, okay? I probably put the 34s a little closer to the 20s than I should have, but, you know, that's all right. It's not that big of a deal, okay? All right, so let's look at another example. Okay, so let's use calculus to sketch a complete graph of this function here. F of x equals 1/8 times x to the 2/3 times 9x squared minus 8x minus 16. Okay, so we're going to start by finding the first derivative and the second derivative. So to get started, I'm going to distribute this x to the 2/3 over, or we could do the product rule if we wanted to, but I'd rather just do a bunch of power rules. Okay, so I'm going to start here with finding the critical points. Okay, and since this is going to be a little more complicated, I won't do f prime and f double prime all in one go. I'm just going to start with f prime, and before I get there, I'm going to distribute this 1/8 x to the 2/3 blah 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 blah. Okay, so we're going to get 9/8 times x. Well, x squared is going to be 6/3 plus 2/3 in the exponent place. The 1/8 and the 8 will cancel to give us x to the 3/3 plus 2/3. And sorry, that should be a minus. And then it will be minus 16 times this. Well, the 8 will cancel with the 16 and leave a 2 times x to the 2/3. All right, so fully simplified now, we're going to get 9/8 x to the 8/3, okay, minus x to the 5/3 minus 2x to the 2/3. All right, kind of nasty, but we'll get there. All right, so now we'll find f prime. So f prime of x, well, using the power rule, I'll have 9/8 times 8/3 times x to the 8/3 minus 1. So that will be 8/3 minus 3/3. All right, apparently I lost a little footage there, sorry. So here's the derivative of the first piece, and we get x to the 8/3 minus 5/3, or 8/3 minus 3/3, which will be 5/3. Then the second piece will be 5/3 x to the 5/3 minus 3/3, which will be 2/3. Then minus 2 times 2/3 times x to the negative 1/3. Okay, so simplifying here, the 9/8 times 8/3 becomes just 3. So we'll get 3 to the times x to the 5/3 minus 5/3 x to the 2/3 minus 4/3 x to the negative 1/3. All right, and so here it looks bad, but what we want to do is to get a common denominator, because if we can rewrite this term here as negative 4 over 3x to the 1/3. So I want to get every term here with the common denominator. Okay, so this term already has it. It's 4 over 3 times x to the 1/3. This term, which we can write as 5x to the 2/3 over 3, it's missing an x to the 1/3. Okay, so that's what we add there to the top and bottom, and here we add in a full 3 times x to the 1/3 on the top and bottom, and we simplify. And when we simplify, for this first term, 3 times x to the 5/3 times 3 times x to the 1/3, we get 9x to the 6/3, which simplifies to 9x squared. Here we get 5x to the 2/3 times x to the 1/3, so that's x to the 2/3 plus 1/3, which is x to the 3/3, which becomes x to the 1, and here it's just minus 4. So we totally end up with 9x squared minus 5x minus 4 all over 3 times x to the 1/3. So sorry that I had to go back and describe this. For whatever reason, my software wasn't recording when I actually worked through this. Hopefully it's still followable, even though you aren't seeing me write out each step. Okay, so after all this, we get down to this derivative. F prime is equal to 9x squared minus 5x minus 4 all over 3x to the 1/3. All right, now this, well, we have two possibilities, right? The 0 is going to cause this to be undefined. So f prime of 0 is undefined. So that is a critical point, because if we go back up to our original function, this is a nice polynomial. This is not, however, since it's a 3 in the denominator here, a third root, this is still continuous. So this whole thing is continuous. However, so I'll say f is continuous everywhere, but not smooth at 0. Right? So this probably means we have some sort of either like a sharp turn, or we have a vertical tangent line. Okay, because 0 is not going to cause the numerator to be 0. Right? When we plug in 0, we'll get negative 4 over 0. So that's a plus or minus infinity. Okay, so this is going to be a spike or a vertical tangent line of some kind. Okay, so now we need to consider what causes the numerator to be equal to 0. So I want to set 9x squared minus 5x minus 4, okay, just to be totally rigorous here. Divided by this equals 0. If we multiply that through, we essentially get 9x squared minus 5x minus 4 equals 0. So just as long as 0 is not a solution to this equation, we should be fine with those critical points. Okay, so if we try to use the AC method here, we're going to be looking for, well, 9 times negative 4, that would be negative 36. So we're looking for factors of negative 36 that will sum up to be negative 5. All right, so we want factors of negative 36. That will sum up to negative 5. So I would say negative 9 and 4, which is exactly what we have here. So again, with this method, we split this negative 5 up into a negative 9x plus a 4x. So we end up with 9x squared minus 9x plus 4x minus 4 equals 0. And then we can factor each of these by grouping. All right, so from here now, we factor a 9x out of the first group to get 9x times x minus 1. And then we can factor out a 4 from the second group to get 4 times x minus 1. And then we can factor out the x minus 1, since they both now share an x minus 1. All right, so we end up with x minus 1 times 9x plus 4. All right, so we end up with x equals 1 or negative 4/9. All right, now, so those are our two other critical points. So the critical points are x equals 1, negative 4/9, and 0, but I'm putting a star next to 0 because 0 is the one that causes it to be undefined. So it looks like that's going to be a spike of some sort. All right. And I'm going to use the first derivative test to tell what's going on, since we have an undefined critical point here. Okay, so let's set up our critical points. So we have negative 4/9, 0, and 1. And I'm going to plug some test values into f prime and see what's happening with f. Okay. Now for plugging in purposes, I'm going to be plugging in values into this version, the factored one. X minus 1 times 9x plus 4 all over 3x to the 1/3. Okay, so for test value number 1, negative 4/9, well, negative 1 should be in this region here to the left side of negative 4/9. So when we plug in a negative 1, we are going to get a negative in this region. Then the negative 9 plus 4, that will be a negative in this region. And then the 3 times x to the 1/3. Well, x to the 1/3 will preserve negatives. So we have negative, negative, negative. So 3 negatives together. That's going to make the whole thing a positive. Or, I'm sorry, a negative. Okay, so the whole thing is a negative. That means f is decreasing on this region. Okay. So then, for the next region, this one's not going to be as nice, but something between 0 and negative 4/9, we could always just pick negative 1/9. Okay, nothing wrong with that. When we plug in negative 1/9, negative 1/9 minus 1, that's negative. Okay. Negative 1/9 times 9 is just negative 1. So I have negative 1 plus 4, so that would be positive. And then x to the 1/3, we plug in a negative, we'll still get a negative. So here, the negatives cancel and we're left with a positive. All right, so in this region, f prime is positive, so f is increasing. All right, now a region or a value between 0 and 1, of course, probably the simplest one I could think of would be 1/2. 1/2 minus 1, that's going to be negative in that first piece. 1/2 times 9, that's positive, plus 4, that's positive, so that's a negative times a positive. And then plugging a positive into x to the 1/3 will be a positive. So we have negative, positive, positive, and so we end up with negative ultimately here. So in this region, once again, f is decreasing. Okay, and then in our final region, I'm just going to pick 2, right? Something greater than 1, and it'll be 2 minus 1, that'll be a positive. This will definitely be a positive, and this will be a positive. So we have positive, positive, positive. The whole thing is positive, so now we've gone back up to increasing. Okay, so we go decreasing, increasing, decreasing, increasing. So that means that negative 4/9 is going to be a minimum. Okay, 0 goes from increasing to decreasing. That's going to be a maximum. However, that is where f prime is undefined. So that's going to, I think I said minimum, sorry. It's going to be a maximum, but since it's an undefined critical point, it's likely going to be something sharp like that. And then decreasing to increasing here at 1, that's going to be a minimum. So anywhere where the derivative actually exists and f prime is 0, that is going to be a smooth turning point. And anywhere we have where the f prime is undefined, that's going to be a sharp turning point. All right, next I want to find the inflection points. So we're going to start with f prime, all right, which is our 9x squared minus 5x minus 4 all over 3x to the 1/3. I could use the factored version. I could use the one that isn't a fraction. I think I want to use the one that's a fraction so that it stays as a fraction. Okay, and we're going to find f double prime. All right, so we're going to use the quotient rule here. So it'll be the derivative of the top, so that'll be 18x minus 5 times the bottom left alone. All right, then times the top left alone, so minus the top left alone, times the derivative of the bottom. Well, the derivative of the bottom, that will be, well, the 3's will cancel, so we'll get x to the 1/3 minus 1, so that would be minus 2/3. Okay, all over, and then the denominator squared. So it'll be 9 times, well, x to the 1/3 squared will be x to the 2/3. All right, now I know this looks bad, but let me show you a quick way to simplify this. See this x to the negative 2/3 here? I'm going to multiply the top and the bottom by x to the 2/3 power. Okay, the reason is when we distribute this through, it's going to completely cancel this negative exponent, and it will let the denominator worry about it. Okay, and then it will also play really nicely with this x to the 1/3. Okay, so and this is basically because x to the negative 2/3 times x to the negative 2/3 will cancel out to be 1. Right, x to the negative 2/3 times x to the 2/3 is 1. All right, and then x to the 1/3 times x to the 2/3, well, that's going to be x to the 3/3, which is x to the 1. Okay, and then, well, it's going to mess up our main denominator, but it will be much better. Right, so we're going to have 18x minus 5 times 3x minus 9x squared minus 5x minus 4 all over, and we'll just have 9x to the 4/3. Okay, and then we can just distribute and simplify. All right, so the 18x times 3x will be 54x minus 15x, and then distributing the minus sign here, we'll get minus 9x squared, sorry, that's 54x squared, minus 9x squared plus 5x plus 4, and this will be all over still 9x to the 4/3. All right, simplifying this further, the 54x squared minus 9x squared will give us 45x squared. Negative 15x plus 5x will give us negative 10x. And, well, we just have the one constant term, so it'll be plus 4 all over 9x to the 4/3. All right, so once again, f double prime of 0 is undefined. Okay, so that that would make it a consideration. However, we already know x of 0 is a maximum, so it's not likely that 0 is going to be an inflection point either. In fact, I would say it's impossible, but that might be a little strong. Okay, so it's already a max, so we really don't have to consider it. We basically need to consider the numerator equal to 0. However, I have a sinking suspicion here that this is not going to ever happen. And that has to do with just the way this looks. So, for example, if we just use the quadratic formula, right, negative b, which will be 10, plus or minus the square root of b squared, which will be 100, minus 4ac, so that'll be 4 times 45 times 4. Well, that's 45 times 16, right, which is going to be 720. So, and then the whole thing is all over 2a. So what's underneath the square root here? This is 100 minus 720. So this is a negative value. So this has no real solutions, or no real roots. Okay, and it's always pretty much going to be positive. If you plug, say, 1 in, you get 45 minus 10 plus 4. That's going to be positive. So it turns out that, and note the denominator here is always positive because we're raising it to the 4 over 3. That 4 will make that positive. So this thing's pretty much always positive. So f double prime is positive everywhere right, except x equals 0, but that's just because f double prime is undefined there. All right, so that means f is concave up everywhere. Right, so there are no inflection points. And this is provided x doesn't equal 0. Okay, so yikes, this is pretty terrible, but we're almost done. Right, all we need to do now is find the intercepts and then put it all together. So the y-intercept, that's when we plug in f equals 0. Thankfully, that zeroes everything out. All right, so 0, 0, the origin is a y-intercept, and that's going to make it an x-intercept as well. So that's a x and y-intercept. And to find the x-intercepts, well, that's where we set it equal to 0 and solve. So here we set 1/8 x to the 2/3 times 9x squared minus 8x minus 16 equal to 0 and solve. So our first solution here is going to be x equals 0. We already got that from here. So now we just need to focus on this 9x squared minus 8x minus 16 equals 0. All right, and I don't think that this is going to factor nicely, because when I look at it, when I multiply 9 and negative 16, you get negative 144, and you don't ever get factors of that to sum up to be negative 8. You can get to 7 and 10, which is kind of close, but you can't actually get there. So it looks like we just have to use a quadratic formula. So x is going to be negative b, so 8, plus or minus the square root of b squared, which will be 64, minus 4ac, okay, all over 2a. All right, so that simplifies down to be 8 plus or minus the square root of 640 all over 18. 640, well, we can take a 64 out of that. So that will be 8 plus or minus, square root of 64 is 8, and so we'll be left with the square root of 10 all over 18. Okay, and we can definitely take a 2 out of all this to get that x finally is 4 plus or minus 4 root 10 over 9. Right, so yeah, that doesn't come out to be perfect, but we can still kind of get an idea of what we're looking for. So x is either, when we do the plus, it's going to be approximately 1.85 and negative 0.96. All right, all there's left to do now really is plug in some of these values. Now we already know that we have 0, 0, so we don't need to plug that in. When we plug in 1, that just becomes 1. Then we get 9 minus 8. So let me just say it's 1/8 times 9 minus 8 minus 16. So that's going to be 1 minus 16. So that will be negative 15/8. And then when we plug in negative 4/9, that one's not going to be as easy to do. So I'm just going to use a calculator for this one. And we will get, all right, so we get negative 0.78. All right, so as we established, this was a min, this was a min, 0, 0 was a max, but it's a sharp one. Okay, and then our x-intercepts, well, one of them is definitely 0, 0, but we also found that they were negative 0.96, 0, and 1.85, 0. All right, so these aren't going to be very nice values. However, we can still just throw these together on a graph. All right, so here's some axes for us. We know we have the point 0, 0. Okay, and then, all right, so 0, 0. So this we know is a max. Specifically, it's a sharp one. We also have the point, well, one of our critical points was at 1, right? And specifically, it was at 1, negative 15 over 8. So notice, I'm not really putting stuff on the y-axis here because it doesn't have to be exact. I'm just trying to get an idea of the shape. All right, and we know that this is a min, and then the other min happened at negative 4/9, so that should be closer to 0, negative 4/9. And at negative 4/9, we had our y value at, it was negative 0.78. Okay, so kind of nasty values, but that's all right. Negative 0.78 is going to be a little greater than the negative 15 over 8. Actually, maybe quite a bit. All right, so let's make it a little more. Okay, and so this is also a min. All right, now these two were smooth mins. This one was a sharp min. So when I bring this in, I can make this guy here a sharp turn. Right, and then we just continue the graph. Because there's no other place where it turned around. And notice we also found that it was concave up everywhere. And this should about do it. Now, again, just where I end up having those x-intercepts, that's just where I'm going to label them. Right, so I'm not being too specific about, right, the graph itself. It doesn't have to be perfect. It just needs to be the general idea. So this is essentially what we have. We have two sort of parabolas crammed together, and we have a sharp turn here at 0. Okay? All right, I know that example is pretty complex. Most of the homework's not going to be that complicated. However, this is what happens when you have sort of an undefined critical point. All right, so that should hopefully be enough to get you rolling on the homework, and I'll catch you on the next one. Cheers.